So anyways, thank you very much and take it away.
Okay. So my name is Thomas Sagi. The company is called Metaprobe and the system is called Modela. I just want to note that this is a totally new system, so you might not have heard about it yet. It's also a very small company. So, okay, so what I'm going to talk about, so I'm going to cover the machine learning lifecycle with the example of customer churn. Now, I do assume that you are a Kubernetes expert and you are also knows machine learning. Like you know what is, a model, cause validation, model scores, etc. If not, then you can just ask me. It's not complicated. And then what I'm going to do, I'm going to explain what is AutoML. So this is kind of mathematical explanation. And then we're going to go why do we have AutoML on Kubernetes, introduction to Modela, then Modela logical design, physical design, like the internal of Modela. We're going to go a couple of CRDs and the demo. And this is in the context of Kubernetes, of course, and AutoML. Okay, so everything is connected. So just to make the talk concrete, we're going to talk about the problem of ML, which is customer churn. So basically, the definition of customer churn, we want to predict. I think it's everybody understand. Predict if a customer is about to churn. And the business domain, of course, it's a SaaS. If you have a SaaS, banking customers, or HR if your employee is about to churn. So usually when you do a manual AutoML or even AutoML, classical AutoML, what you do is you collect your features, which are the customer, customer service call. You train a churn model. You deploy the churn model, and you make churn predictions. And then you use this customer data basically to make the churn prediction. And then you take action like offer a discount or deal. And once your data change or time going by, you want to retrain your model. So the business goals. So if we look at the ML lifecycle from this perspective, basically we start with the business goals. In the business goals, what we define is so we have the business problem, so we want to understand why our customer is churning, and we have a KPI, which is how many customers has churned. Then we frame the problem, which is the customer churn. We want to explore our data, which means that for example, we can connect to a CRM system or another system to see what system we can get the data from. We prepare the data, we clean it, we see missing values, etc. And then we start the ML process. So the ML process, the first thing we want is we're going to split the data to training, validation, and test. This is the classical ML process. We're going to train one or more model. For example, SVM, XGBoost, deep learning, etc. And then we're going to iterate on the models and the preparation. And at the end, we're going to use the test data set to test our model. If it is good, based on our metrics that we define, we're going to deploy the model to production. For example, we're going to package it as a Docker container, deploy it on Kubernetes cluster, and then we start the life of the model. So we're basically going to monitor our model for data drift, and as well as regular, system monitoring, CPU, memory, etc. And all of this is the one big iteration. So now that we have different data, we see what our results were, we take the action, and then we start the process again. So the ML is a never-ending iteration driven by the data. So now recent concern that in the ML with data scientists is basically unit testing. So there's something called MLOps, and which is coming from DevOps. So DevOps to use unit testing or automatic testing. And there's different unit tests because it's a database thing. There's a different test that we want to run. So we want to run a data unit test to make sure that our data is correct. So we, for example, our average customer age should be from 20 to 60 or something like that, or other that we don't have nulls in the value, etc. Once we train the model, we have a model unit test. So, for example, you want to make sure that accuracy, is above 80%, or the model latency, etc. Then, once the model in production, we do the same data test on our prediction data. So we get data to predict. We want to make sure that it has the same, the same quality as our training data, and we don't make like false predictions, because this is like the worst that you can do is the silent failures of ML models. So because everything looks nice, but we give like bad result, which is very bad. I mean, should be avoided. And then, of course, the models are in production, so we want to do a model drift test. So basically, here we compare the distribution of the models in production of each feature to our training distribution in order to see that we didn't have a training serving skew. Okay, and the recent concern, there's more concerns. So recently, that we don't want to treat the models as black box. So, for example, for our data, we want to identify if we have a bias in our data sets, test for biases. For each model that we are creating, we want to explain it. There's something called Shapley value. So we want to make sure either we have a global explanation or local explanation. So we either explain the model behavior, etc., like feature importance, what are the important feature, or we have local explanation. So we can do Shapley values for each prediction to see what are the contribution of each feature to our prediction. And then once the model in production, of course, another concern is the CI/CD. So this is like the DevOps. We want to automate the process and automatically promote models between our unit test environments, etc. Okay, and if we are looking at it, so we have the data ops, the machine learning ops, and the ML operation. Okay, so now it's AutoML. Okay, so what is AutoML? So the AutoML is basically, we want to automate the task of applying machine learning. And why we want to do that? Of course, productivity. So AutoML basically replace the human time with machine time, and the machine time is, first of all, it doesn't have 401k. It can run. It's very cheap if you look even at machine in the cloud, which are expensive, but it's very cheap compared to a data scientist. It can try a lot of models, but it can cost a lot because it need to train hundreds of models in order to reach a good model. So if we look at the AutoML methods, basically we have the AutoML. So the current AutoML field of research, this is in research, it is the first separation is between classical AutoML and deep network AutoML, and they are looking for different stuff. So the DNN AutoML is called NAS, which is architecture search. So here you don't search hyperparameters. You basically search the model architecture. It's hyperparameters, but they are referring to the model architecture. So, for example, how many nodes do I have per layer, like optimization function, etc. So this is called NAS. The classical AutoML, which is what Modela are using now, is basically searching hyperparameters problem. I'm going to explain how it does that. So here we divide the methods to a model-based, which means that this is a Bayesian optimization, which means that we use a surrogate model in order to direct the search, or a model-free, which what we do is basically it's a brute force kind of search, but we can allocate our budget to different phases in order to not to use a lot of budget, because this is the main problem of AutoML. Okay, so this is a definition of the AutoML hyperparameters optimization problem. Now the key problem with AutoML is that this is like a black box. So every model that we train, or the training function, we cannot optimize it in regular way because it's a function of our data preparation pipeline, our algorithm, and our hyperparameters. Now, the hyperparameters depends on the algorithm, right? So if we select SVM, we have different hyperparameters. Of deep neural net, different hyperparameters. So we must treat it as a black box problem. And the other problem is that we must evaluate the black box each time. So it's a very costly process. It can cost us in CPU, memory, etc., and also in time. And because we need to run hundreds of models or even more, and also like a single model, like if you want to train a DNN, especially with DNNs, they have a very expensive hardware, and it takes a lot of time to train them. So it can take us, for example, half a day. So we want to minimize the number of time that we actually do the training. So this is why AutoML, the core AutoML, this is why the field exists, to find the most efficient search. Okay, if you any AutoML problem is a problem. So here it's going to be kind of mathematical, but I'm going to try to make it like minimal. Okay, so the first search that we have, like usually you're going to do like a regular data scientist, we know AutoML system is going to use either grid search or random search. The problem with the grid search is that you only search the point on the grid that you defined. So you might waste a lot of time on points that doesn't have any meaning. I mean, it doesn't help you. And also it's exponential on the number of parameters. So it's going to take you a long, long time to search because there's a lot of combinations. The problem with random search is basically that you don't learn from history. So you just travel around the models and you're going to waste a lot of training on points that are not relevant. So both of them are what we have. Like random search is good because you can do, if you have a parallel system, you can cover a lot of models, but still most of your computation is wasted. So the field of research in AutoML come up with this is the base model, which is called sequential model-based optimization. I don't know if you heard about Bayesian optimization, but this is the definition of the problem. So because it is model-based, what we do is we choose a surrogate model, which is the Gaussian process regression. And what is special about this process is that it doesn't give us a point prediction, but it gives us a Gaussian distribution prediction. Okay. So what we do in the search, and then in addition to that, we're going to make prediction after each trial, and then there's something called an acquisition function that's going to score the prediction, and this is a Bayesian acquisition function, and then it's going to give us the best point to search next. Okay. So if you see here, like in this first iteration, we basically made the search. We evaluate the function fx in the observation. We use the Gaussian process model to make this Gaussian prediction. This is like the mean, this is a black line, okay? And the dotted line is our real function, okay? And then we use our acquisition function to score this score our all of those Gaussian function or Gaussian scores. We got the best point here. And then in this iteration, we run another FX, we run another evaluation, we update the Gaussian, and we run against the acquisition function. We got the best point. Now, we see that the acquisition function is moving between exploration and exploitation, which means that at the first phase, at the first phases or the first 20 models, the Gaussian process will look like random, okay? Because it doesn't have it's gathering information about the function. So it's kind of exploring the space. And then it moves into exploitation. So it kind of like know where is the minimum. So it's kind of start getting experiments near the minimum, okay? And everything like that is up to a budget, of course. So budget can be a CPU time or, actual clock time, etc. or cost, okay? Okay, so the next family of algorithms which are started around 2015, like the Bayesian optimization is a very old technology, the Bayesian itself, but it was started 2015, 16. It's starting to appear new model-free methods, which is kind of a brute force. The idea here, most of the models are based on multimodality. What multimodality means is that we use our data in order to decrease modality and then try a lot of simple models and then select like the best, X, the best like third, and then give them more budget or give them more modality until we reach the best model. So for example, here, we're going to train 9 models on 9 iterations, okay? And then we're going to train another 20, we select the best third, we're going to train them, give them more budget on 27 iteration, select the best one, and do a full training. Now, this algorithm, this is the paper called Hyperband. There was a company which was acquired by HP called Determined.ai. And this company basically commercialized this technology. I mean, this technology, this guy is like the founder. If you want to read the paper, it's more complicated, but I don't want to go into this because this is kind of research. Okay. However, so this is very famous picture. However, if you deploy ML into production, you know that the ML training part is very small part, right? So it's just this box, but we need to, we are concerned with feature extraction, the actual collection of data pipeline, training pipeline, serving infrastructure, monitoring, a ton of stuff that we need to be concerned about. And it's much more complicated than regular ML ops because we have the data, right? So the actual life of a model starts when you put it in production and know the training, okay? Because the model is basically seeing real life data and then it's kind of start drifting usually, and you want to retrain it. And so this is the main concern. This is why it's like a never-ending iteration. So like AutoML can be very helpful here. Okay, so what we need is basically this. Okay, this is why I put the picture. So we need AutoML for all those parts, not just the training. Okay. So if we look at the current AutoML landscape, I just want to give you all the products, not just Modela. Even though Modela is it's very still not on these charts. So basically, you can either use open source tuning models. So those Bayesian optimization processes that I explained, they are exposed as a standalone server. So for example, if somebody knows about Kubeflow, there's something called Katib, which is a model tuner. There's also RayTune. I think that Google offer Visor, which is their tuning service, not just for AutoML. And then Optuna, which we use. There's AutoML toolkits. So if you're a data scientist and you just want to use AutoML, on a notebook or something, there is like automatic AutoTipot, auto scikit-learn, py-caret, and for deep learning, this AutoGlone and AutoKeras. And then there's offering from the big cloud providers. I mean, there's 2 independent companies, which is Cloud Natural, which is H2O.ai and DataRobot. Very, very complicated and very, very nice products. I think they're amazing. And then you have, of course, the offering, which is also quite comprehensive from the cloud providers, SageMaker, Vertex, from Google. All of them are very, very nice products. A lot of engineering time. Okay, so here this is like an explosion of features. But I just want to give you a checklist of what to look at when you test an AutoML platform, because some platform doesn't have what other. So if you look at the data operation, basically you want a platform that will support automatic EDA. Now, any feature that I say here, you can add an automatic as a prefix. Okay, so you want to, for example, automatic EDA, automatic reports, automatic data unit tests, automatic storage management. Okay. For feature engineering, you want automatic feature selection, automatic skew detection, automatic missing value imputation, automatic handling of imbalanced data. For training, this is the traditional AutoML. However, you want to have experiment tracking, automatic explainable AI, which is not supported by the traditional regular optimization. You want automatic visualization on your model, automatic assembling, etc. Once you're in deployment, this is close to Kubernetes, then you want automatic promotion. So for example, you have a canary models or shadow models and live models. You want to track them both and do promotion between them. You want to log your prediction, automatic scaling, which is supported by Kubernetes, automatic system and data monitoring. For example, Prometheus, like system metrics and model metrics, and automatic drift detection, and of course retraining. Besides that, there is like, if you are managing a platform, so if you're in a platform team, you have like a data scientist, data science team, and if you're in the platform team, of course you want those features. So you want automatic scaling, like for your one-time environment, you want to support different training hardwares. Preferably it's going to be a multi-cloud or not, because each cloud is going to have its own platform. You want to offer automatic one-time cost optimization. This can be very expensive. So, for example, you want to train on spot instances. Preferably the platform should manage its users. With regards to AutoML, there's something called AutoML governance, which means that the model doesn't go into production without somebody which assure that or which sign on them. Automatic auditing, on automatic security, and of course the platform should offer gRPC API and alerts, etc., and a Python and Java SDK. So now we enter Modela. So what is Modela? Why is it such it can be seen as a crazy idea? I don't know. So basically, when I designed or thought about Modela, I was seeing Kubernetes was just starting. It was when CRDs were called TPR. I don't know if anybody knows that, but I was seeing that Kubernetes is an infrastructure automation, right? And it can be extended. So why not extend Kubernetes into machine learning automation? Okay, so we're gonna make this jump, right? So if we see what enables this infrastructure automation in Kubernetes, so first we have a declarative no-code environment. So Kubernetes resources, I assume everybody knows they have the spec and the status, and the spec is fully declarative, and we have this operator pattern. So every CRD or every core CR as a controller that try to reconcile or reduce the drift between the spec and the real world. So we have this in Kubernetes. So this is like the core automation that we have. It's a very mature code base. Of course, Kubernetes is multi-cloud, etc., and it has a great ecosystem of tools. But the key idea is that this declarative design of Kubernetes, which is the core of automation, which this is like the main innovation of Kubernetes. So if we like, there's companies now that are, like, for example, Upbound or Crossplane, that are like automating, want to replace Terraform with this design. And what Modela does, it's offering you an ML automation based on this design. So what is Modela? So Modela is basically this CRD only ML platform, where everything that you saw in this in the flow diagram or in the ML lifecycle is a CRD. Okay, and of course, since it is like that, so it's a no-code platform. You do not see a single line of Python in the full lifecycle. It's fully declarative. All of the logic in Modela is inside controllers. I make a distinction between a controller and an operator. I mean, operator is a controller, but not all controllers are operators. So operator for me is mainly something that has operational knowledge, like SRE stuff, and controller is more of like in charge of the CRD. And then of course it does support data training and inference. We're going to see more, and it's an end-to-end ML platform. So you don't need to use any other tool besides Modela. So we don't need to understand any open source tool or any other tool. And you can say in this conceptual integrity. And of course, it's part of the Kubernetes ecosystem. So you enjoy, Kubernetes, all your other tools. So for example, like a data set, that's an example of a data set. So you see that I'm using kubectl, get data sets. I see like the rows. So this is a data set CRD. I manage it like any other Kubernetes object. So the Modela tenant, okay, so now I'm going to describe the CRDs in Modela, and I'm going to connect them to AutoML. Okay, so Modela is a multi-tenant system, so each tenant is a namespace, and then you have the tenant CRD, of course, and then each tenant include a account CR, so you can define user account, you define connection. So Modela can be connected to different systems, either external databases like Snowflake, SQL Server, Postgres, MySQL, etc. Notification system. There's like 74 connections. Facebook, Twitter. There's a lot of connections. Bucket is an abstraction of the storage. So Modela is a stateless system. It is designed around the idea of a data lake. All of the components are in the data lake. It has a notifier. So a notifier CRD. So this is the bucket. The notifier CRD you can connect to other. You can use the notification like Slack, etc. There is a namespace for now. There are CRD that are namespace related. So, for example, the lab CRD is used to define your training area, which is the lab. The serving site CRD is used to define where you're going to put the predictor. This is the live traffic. And then for each ML use case, Modela has a data product CRD. And of course, everything here is automatic. So it's all, those are all state machines that run by controllers. So you just leave the system and it's going to take care of a lot of stuff. And then we have two special namespaces, the Modela system, where all the Modela controllers and everything is running, and the Modela catalog. So the Modela describes itself. So this is where the metadata about Modela itself exists, like what algorithm, what hyperparameters, etc. Okay, so in the data product CRD, we see that we have like different API groups. We start with the data API group. So here we have something, I'm going to explain the core CRD later, but here we have the data source, which define our data source, like for example, for churn prediction, the CRM system or CRM database. We have a full description of a schema, a data set, which is metadata about your actual data, can be stored in a database or in a cloud. A data pipeline is the actual, so you can prepare your data. So this is a declarative way to prepare your data. It includes around 230 functions that you can use declaratively to data preparation, and it's composed of recipes. In the training, this is the AutoML. So we have the study, which is manage the AutoML process for a single run. The model, as I described, define declaratively our pipeline and model and hyperparameters. I'm gonna explain it later. And then we have reports. So there's a report CRD for model, study, and dataset. And the model pipeline is our CI/CD. In the inference, this is the prediction. Basically, we have the predictor CRD, which define how to put model into production. So it takes care of a lot of stuff. Again, I'm going to dive deeper later. Prediction is batch prediction. A data app is a dashboard that is generated based on your predictor. And a feature histogram CRD is basically for real-time prediction, it stores the actual distribution of each feature. So if we look at the Modela workflow for training, basically to train model, for example, the churn prediction. So first I'm going to define the churn data source. Then I'm going to define the churn data set. So I'm going to upload my data or tell Modela where to get the data in a data set CR. And the state machine of the data set will actually create the reports, do visualization, profiling, etc. We use the connection CRD. So the data set uses the connection to get the credential and connect to external system. One of the stages of the dataset state machine is to generate a report. And when it's done, it's going to use the notifier to notify you. So Modela is kind of a synchronous system. You just let it work, and you're going to get like in Slack, I finish this report, finish this dataset, or you get like error alerts. There's an alert CRD that is generated by the other CRDs. And then and once you have the dataset, you can run the AutoML. So the AutoML is run by the study. Basically, the study used the data plane. We're going to see what it is to run a session, AutoML session or version optimization via Optuna. During this session, it's going to create the Optuna going to tell us, going to start sampling this in a version way, the best models, that we want to try next. And each model is a Kubernetes job that use a trainer container, which actually contain the code to convert the model into Python, again, automatically, do the training, do cross-validation, imputation, etc. It's a full pipeline, and then get the results, put them back in the model. For the serving part, again, we have the model that we want to put in production. So this is the live model. We're going to run the predictor CRD, the predictor, which is going to start our inference server. And this inference server is going to maintain a live feature histogram that's going to update based on the predictor that we get. I'm going to go into the predictor later. And then we have the data app, which is the dashboard that I said it generated. And again, we can run batch prediction or clone prediction. So this is the Modela physical design. Now this slide I'm giving usually two presentations, one for data scientists and the other one for a Kubernetes engineer. So you are the Kubernetes engineer, so I assume that you have deep Kubernetes knowledge. So basically, if you look at the Modela design, we have the Modela control plane and the Modela data plane. The Modela control plane run all the controllers with the storage in the actual data lake is in S3. And then what happens is that each Modela object has a TTL. So there's a garbage collection process. They take the live object from etcd and put them into Postgres. And then everything is managed in the data lake in S3. And then on the worker node, we actually either run a training job or put the prediction cell. So the physical concern of compute, basically we have everything is a Kubernetes job, scheduled by the Kubernetes scheduler. Modela define a workload CR, which is like different CPU or GPU, etc. And then it define a managed images. Basically the container that we have. So for example, if you have deep learning, it's a different container. And of course, the predictor CR is translated into deployment for the predictorate or the models. So the concern of storage, so basically all the Modela objects are stored in etcd. As I say, they are garbage collected into Postgres. The prediction themselves are stored in SQLite on each predictor. And there is a S3-like bucket where we store the artifact of Modela. And the idea is that it's a stateless design. So Modela doesn't have anything inside it. Just everything is like in the data lake. So if you look at the Modela predictor, it's a custom-made Go gRPC server. It's inspired by the Golang Gene framework, if anybody know about the design. So we have a bunch of middleware such that each one handles the prediction and it provides a lot of functionality. So first we authenticate a prediction, then we log it into SQLite. We do prediction validation. We update our counters for Prometheus monitoring. Then we log the real-time drift into etcd. We update the feature histogram into etcd. And then based on our model, we can route traffic either to the live model or the shadow model. So we support request validation, drift detection. All the parts that I show in the flow is supported by the Modela prediction. And of course, there's the Modela operator. So here, this is a separate components from Modela, because this is the first thing that you install, and basically this is managed Modela itself. So Modela also manages itself operationally. So this is an operator. So basically you install it, there's a Modela CRD, and it's going to manage Modela like upgrade, backups, etc. And if you can look at it. Okay, so now I'm going to go over the core CRs. Okay, so the first, this, and also I'm going to tie it to AutoML. So basically, okay, so if we want to use Kubernetes as our machine learning automation, ML automation, the first core CR that I think should exist is the model, right? Because we want to automatic training, automatic testing, automatic validation, automatic evaluation, explanation, etc. We want to automate this, and if we want to do it in Kubernetes, we must have a custom resource and a controller. So the model custom resource is basically contain all the definition to build a trainable model. So it has a full definition of a feature engineering pipeline, a feature selection, and the scikit-learn, and then the full definition of all the scikit-learn, possible algorithm, XGBoost, and IGB. Okay? It also has a definition on how to do cross-validation, which is different between use case and use case. And this is also designed by Modela. It has a definition of handling imbalanced data. So it has different imbalance options, so you can control that if you are a data scientist. It stores all the ML metrics after the training based on your task. So you have metrics for classification, like AUC, ROC, or regression. It stores the confusion metrics, both the test metrics and the train metrics, and it stores the feature importance, Shapley values, etc. Some of those, like visualization and Shapley values, stored on the cloud in the data lake. But the model is a URL that points to that. So for example, if we see here in the picture, this is a logistic regression, and those are all the hyperparameters, and those are part of the model CRD. So you automatically get experiment management, etc. And you get the AutoML, because it's automatic training, you don't need to worry about anything. And again, the feature engineering pipeline, we see that this is a complete feature engineering, like a complete pipeline, which were designed by Modela during the study. So the AutoML, if we tie the AutoML to Modela, we have the study custom resource. So the study custom resource is basically the AutoML orchestrator. So each state machine manages the actual AutoML process. Okay. So we start with a data split. It's gonna split the data and store the splitted data as Parquet file in our data lake. Then it starts a two-phase optimization process. Either the first phase is feature engineering, so it's going to find the best feature engineering pipeline and the best features, basically. And then based on that, it's going to do the model, which I explained there. It's going to do a Bayesian search or model-free search, or hyperband. Based on that, and then it's going to run, it's going to search hundreds of models. And of course, we automatically get experiment tracking because each model is experiment. There's support for ensemble, so it's going to select the best models from a search and try to make an ensemble, stacking ensemble of them and treat them as models. You can define early stopping, baseline models, like if you want to compare the models that Modela create to a default hyperparameters model. You can constrain the search by maximum time, maximum model, and minimum score. And there is support for model unit tests. Now we have a data source CR. So a data source CR this is support the data format. So you can define the format of your data, either a database or a CSV Excel file. For each, we're going to analyze the actual data source, and we're going to infer the schema. Like we're going to infer the data types, and in the future we're going to generate the data unit test. But there is already support for a dataset level, column level, and file level unit test. I don't know if you heard about the library called Great Expectation. So there's a trend of data quality, and Modela is it within it. The actual data is described by the dataset CR. So a dataset CR defines the data location. This is the actual data. Now Modela, the dataset CR automatically will do profiling on your data. So you get statistics. It's going to use unsupervised model to create an outlier. So you get like an outlier file. And then it's automatically going to generate the visualization and create a report on each new data set that you get. And it's going to run the data quality checks. Now we're going into inference. So we have the predictor CR. So this put your models in production, as I described before. We have support for live and shadow models. We set up predictor deployment, etc. There is a test like data drift test that are automatically created for you, and it's basically done. You can define like every 1 hour you close an histogram, and then you run the live histogram against your training histogram, and you're gonna notify it if there is a drift based on the time. And then, of course, it has built-in support for integrity. So it's going to make sure that the prediction data adhere to the data source schema. It's going to log prediction. And it is connected to the Kubernetes API server to watch for changes in configuration. And above all of that, we have the data product CR, which, as example, it defines the data product. So this is the Kubernetes. This defines a Kubernetes namespace. We have a definition for default training and serving workload, a default serving site and default lab, and of course the governance. So if you can see here, this is from the data product CR. So you have the default lab, you have the definition of a serving resource, the default one, the default serving site, etc., and the task, which is okay.
All right, I'm going to take over from here. Can y'all hear me?
Yes.
Let's see if I can present.
Okay, I'm stopped present.
Oops. All right. All right, so can you see my screen?
Yes.
All right, so my name is Liam. I'm the other developer on Medela.ai, and I'm just going to take you through a quick demo of the platform. So first, I'm just going to cover quickly how you can install it. As you saw before, there is an operator. So all you need to do is apply the operator resources and the operator CRD, and that's automatically going to install Medela Bootstrap and installation, as well as make it accessible on your browser with Nginx. So once you install Medela, all you need to do is head to medela/app.localhost. And once you log in, you're going to be at the tenant dashboard, which contains all of the tenant level resources. So the most important resource in the tenant, obviously, is the data product. And this resource creates a namespace that groups all of your machine learning resources. So let's get started by making our first data product. Today, we're going to be doing a churn data set. So if you wanted to, you could configure the default settings, default resources, etc. But let's just start by making our data product and going inside. And once we're in our data product dashboard, we're able to interact with all of our machine learning specific resources. And the first thing we need to do in the process of making a model is to define our first data source, which is the schema for our data set. We don't need to configure anything. It's already set to binary classification. Just upload your data set. Yep. Send it to the data plane so it can look at all of the columns, their names, and their types. And yep, it's going to take a second. Select the target column, which models we train will predict on. And let's just create our data set. And it's going to submit a dataset resource to the cluster, which now the dataset controller is going to start a job to do an EDA on our dataset. So if we check out our jobs tab, we can see that the job has been created on our cluster and is now running. But since we don't want to wait for this to finish, it's about 1,000 rows. Let's just head to our other namespace where this dataset is already finished and ready to be used. So if we want to check out the profile Medela generated, all we need to do is go to the Profile tab, give it a second to load. Yep, just give it a sec. And now we can see our file size statistics, our column level statistics, including the distribution for each column, the class distribution, numerical distribution, etc. And all of the visualizations are produced during the profiling process. And if you wanted to share this with somebody else, it also does generate a report, a PDF report that you can share, and it also contains these visualizations. So let's not waste time and make our first study resource. And this is going to start the AutoML process. Medela automatically will select your data set. Let's select the objective metric, which Medela will optimize. Let's also configure the number of models that are going to train simultaneously, the maximum number of candidates it's going to train during the optimization process. Let's also configure our feature engineering search to have 8 maximum candidates and 4 parallel trainers. And there's also a lot of other options you could configure, like feature selection, baseline models, ensembles, etc. But we're not going to look at that today. So, because we want to look at the study. So let's submit it. The first thing Medela is going to do is split the data set into testing, training, and if specified, a validation data set. So if we check out our jobs tab again, yep, it has been started, and it'll only take a second to complete. Yep, now the data set is split. And now what the study controller is going to do is start sampling models with different feature engineering configurations to optimize our feature engineering using Bayesian optimization, given like the number of constraints we specified, which in this case, it's the number of candidate models we decide to train for this phase. So if we go into our model spec to see the different feature engineering pipelines it's sampling, you just go to the small diagram and we can see it's testing different imputations, scaling, encoding for categorical variables, outlier handling, and more. And each of these models is different, and what the system is trying to do is see how these different configurations affect the final score, so it can continue to optimize and move the best feature engineering configuration it could train into the next phase, where it's going to search for algorithm and hyperparameters. So we're on our last batch of training here with 4 models. And if we wanted to, this is also a native Kubernetes object. So there's a big spec here, which contains all our feature engineering pipeline, our status, our spec, confusion matrix, and a lot of stuff, which is represented in the interface here. All right, so it's almost done. One more model, just give it a second. All right, so it decided that this feature engineering pipeline was the best with all of these encoding, scaling, imputation, etc. And now what it's going to do is start trying new algorithms and tuning the hyperparameters of algorithms it already sampled. And this can be a pretty long process. You could specify 100 models, and during this Bayesian optimization process, it'll try to find the best model it could produce, given the data set and all of the algorithm and hyperparameters that were available in the catalog. Since we don't want to wait for this to complete, let's just go to a finished version of this model. You can see it's already completed 100%. If we want to, it is also a random forest classifier model. So all of the information about the model is available on our sidebar here, all of the metrics, charts, etc. To get a more detailed view, we can also go inside the page, check out the train confusion matrix, test confusion matrix, all of our metrics, hyperparameters, feature engineering, and all these other visualizations. And we can also see what features were the most important. So in this case, it was the number of customer service calls that had the greatest effect on the prediction output. All right. So under normal circumstances, to deploy this model to production, all you would need to do is select the model, hit release, and that's going to create our predictor custom resource. Since I've already done this, my predictor is available and ready to make predictions. And the predictor deployment essentially serves a live model API for the model. So all we need to do to make a prediction is head to this tab, and we have all of our columns, their features that we can play around with and make predictions. So let's make a test prediction now. Yep, it said no. But if we up the number of customer service calls this theoretical customer made, then yeah, it was a churn. If you would like to share this model with non-technical users, there is also the data app resource. And this is essentially a Streamlit application. So if we go here, we have Modelo automatically creates a Streamlit dashboard, which if you share it over Ingress, you can easily give it to non-technical users. Yep. So let's just make a test prediction. Said yes, because there was like 5 customer service calls. Let's dial it down. And nope, probably not. Probably not churn. All right. So this essentially covers all of the resources that I'm going to show you today in this demo. If you want to dive deeper, I highly recommend trying it on a local Kubernetes cluster, as Modelo supports, can probably support your data set if you'd like to play around with it. All right. So I'm going to hand it off back to Tomer to finish our presentation.
Okay, can you see me? Okay, so again, the next steps, if you want to try Modelo, you can install it on any Kubernetes cluster, on any cloud, or on your local cluster. And then you just need to install the Modelo operator, which is here. Okay, so the resulting system. So basically what we saw an end-to-end AutoML system with basically that supports all the functions that an AutoML system with not a single code line of Python. So Modelo is very the design very adhere to the no code. So since it's a declarative system, of course you can start applying GitOps, etc. All the other Kubernetes tools that exist today. It is a fully Kubernetes native. It's based on CRDs and controllers. I think it's very cost effective because you can run it either locally. It's not a SaaS-based offering, so it's kind of like a Postgres server. You can run it locally on any hardware, either yours, on-prem, or managed. It's a multi-cloud. It can run in a private data center, etc. It is completely private. So if you have a sensitive data, you own your data sets and models. What Modelo will do is basically make all this iteration of all the flow of ML much faster. But it's up to you. I mean, it's your own hardware. So Modelo is going to manage your data set, but you have control on the models. And all the models are open source in nature. So it's either XGBoost models or scikit-learn models. And it's a single tool. You don't need to understand any other tools. And since you understand Kubernetes, I assume, you already understand Modelo, I think. You just need to switch from a pod to a model. And you understand Modelo. It's kind of... and then, and it's built, of course, on top of a mature enterprise-ready open source. So you already enjoy all the work that was done on Kubernetes itself, from maturity standpoint and from feature standpoint. It is built under the hood using scikit-learn and pandas, and XGBoost, etc., all open source. And it automates the infrastructure, data, training, serving, and it is scalable and highly available because Kubernetes is scalable and highly available. So Modelo is built on top of XCD, which means that it's automatically scalable if you design the XCD correctly. And of course, it has out-of-the-box integration with the wider Kubernetes ecosystem, like policy engine, storage, etc. There's so no. If anybody has a Q&A, would love to answer.
Anybody have any questions or?
If someone wanted to play with this in not the demo mode, but like an exploration kind of mode, do you have like a getting started guide that we can go through and converse around, I guess?
Yes, absolutely. Did I say here? Yeah. So absolutely. Also, you can either join the Slack chat, the Discord, or you can send me an email if you're exploring it. Yeah. So there's a guide on how to install a Modelo operator. Also, I did mention that Modelo comes with the built-in public data sets. as a CRD. So yeah, so there's like different domains. You can do a kubectl get public dataset, and you can download the public dataset and start working on Modela. You don't even need the data to work with Modela. Okay?
Nice.
Yeah, it's a very elaborate. It's a big. There's like 60 CRDs. I try to cover every. I mean, I didn't want to leave anything on the floor, which I see today in the market is very fragmented. There's like different tools for different things. So I tried to build Modela to be, really end-to-end automatic system.
Sure. I was gonna say, what kind of, I mean, it sounds like you can almost do anything with it, but I mean, do you have any like use cases where people have actually used it and or yourselves, and what do you say as far as it's being compared to other type systems? Because it looks like it's quite an extensive ecosystem. It's quite amazing.
First of all, thank you. Sure. Okay, so first of all, it's very young. So we don't have a lot of customers, I'll just admit. I mean, I'm an engineer, so marketing wasn't the strongest point in the company. And I got a lot of slack. Usually you have this, you build the MVP, and then you try to get customers. I did the opposite. I didn't feel ethically to release a system that you need to code. Okay, like if you need Python, then for me it defeats the purpose of Modela, because then you need the expensive engineer, and then you might as well run manual autonomy. So this was my own design. But Modela was designed mainly for business type ML. So it's mainly a tabular business data. Okay. It does not support, currently it does not support this. It supports NLP using TF-IDF. I mean, using I call it a regular, but it doesn't support, for example, transformers, and it doesn't support vision. Okay. It does have an API for deep learning. So the API is there. So one of my design constraints is that I don't want the Modela API to change. It's kind of like Golang, where the language was freezed in 2012. Okay, so this is why it really doesn't have customers, because I want to iterate on the API myself, and then I'm going to freeze the API. So the API has support for deep learning, but Modela doesn't yet support deep learning. Mainly because it was the request. If you want to do vision, I mean, we can do something. I mean, we can do it. It also should have some. Also, the plan is to support transformers. This is the plan. But if this is a user request, then we can accommodate it. But the main thing is regular tabular data. This is the main use case, and this is like what is offered today with a lot of AutoML systems. Azure ML.
What type of resource requirements? I mean, you have quite a few things, moving parts in this. What is kind of your thought as far as the kind of the cost of entry, just getting the ecosystem set up, and then what you have then running of it?
Sure. So again, it's a fully scalable on the hardware. So I tested on my machine. I mean, I have 32 gig, but I tested it on a laptop with 16 gig. So you can run it locally with Docker desktop. Of course, it depends on your data set. What happens is that when Modela does the data profiling, it has a very strong CPU cost. Like it does, for example, correlations, which require a lot of CPU. So you can get this CPU spike, and then you get out of memory. Okay, and we saw that. But what happened with Modela is that you have different workload CRD, so you can define a large workload and give it to a job. Okay, and then basically Modela, we're going to use the Kubernetes resource, requirements, limits. Okay, and then assign each job. So basically, so it depends on you. You can assign different level of workload to different parts of the process. So if you know that your model are easy, you don't have a lot of data, you can define a small workload. If you have a lot of data, you can assign big workload. Okay, yeah, so it's up to you. So Modela currently doesn't automatically manage the workload for you. It doesn't watch the job and then change it. Okay? But you can define your workload. But we go back to the original question. You can run it on a 16 gig laptop. Just try, small data set. Or you just stream your data set. If you just want to try it. If you want to run it in production, of course, like any other Kubernetes cluster in production, you should give, you should run, 3 etcd, high availability. You want to reach our availability. And then, each one of the predictor, you can define, it does support auto-scaling. So, it creates an HPA object.
Hey, I don't mean to interrupt, but I'm going to leave a link to our quick start guide in the chat.
Perfect.
Check it out. It contains a pretty straightforward guide on how you can install it, make models, and use Modela. So,
Thank you.
Sure. Okay, yeah. So you can start. You can try it on a laptop. And again, we are at the point that you can actually either join the Discord or the Slack, and we can answer the question. So if you have any problem, you're going to get immediate response, and we work 24/7. If you need,
any other questions from the group before we? Anybody else? Well, Tomer and
if you have
Liam,
any AutoML question, is awesome.
what was that?
If you have any AutoML question, also.
Yeah. Any other questions? If not, I guess then we could do offline with the Slack and also his email there. But let's give Tomer and Liam a round.
thanks for having us.
Yeah, thank you very much.
Really appreciate it.
Very informative. And again, thank you and thank you all for being here.
Thank you.
Okay, thanks a lot.
Bye.
Bye.
Bye.